Hello and welcome to section 6.6, Rational Exponents. Basically, we're going to be applying the properties of exponents and radicals that we already know to be able to simplify expressions that have rational exponents or fractional exponents, okay? So we're going to learn how to go back and forth between exponential and radical form, and then we're going to be able to use those different things to simplify. So here's the basic concept. If I have a number to 1 over n, so like if I have 8 to the 1/3. For a real number b, and n is a positive integer, so b to that fraction is equal to the radical, where n is the index, and that 1 is like the exponent on the b. Okay, so 8 to the 1/3, the denominator of my fractional exponent becomes the index, and then this number, my base, my 8, goes under here, and the 1 is technically there as an exponent, but since it's a 1, we don't have to write it. So 8 to the 1/3 is the cube root of 8, which of course would be 2. For example, 27 to the 1/3 is the cube root of 27, or 3. Negative 16 to the 1/2, that 2 is my index, so that's a square root of negative 16, which would be 4i, thinking about our imaginary numbers. So how would we write a to the 1/7 in radical form? So this is rational exponent form. I want to put it in radical form. This is what it would look like. A to the 1/7 is the 7th root of a. And I can go the other way, right? Here I have a radical. I want to write it in exponential form. Exponential form of the square root of w is w to the 1/2. Again, because the index here is 2, even though it's not written, and the exponent here is 1. All right, you guys try this one. All right, the answer here is C, the cube root of a. And try this one, the 5th root of x. All right, in exponential form, that's x to the 1/5. All right, so now what we're going to do is we're going to talk about evaluating expressions that have rational exponents. And there's different ways you can do this. So I'm going to show you two methods here in this first one. I have 49 to the negative 1/2. So this negative 1/2 is my exponent. My first method is to start with the exponent rule. Okay, well, negative exponent means reciprocal, right? So 49 to the negative 1/2 is 1 over 49 to the 1/2. 49 to the 1/2 is the same as the square root of 49. The square root of 49 is 7, so that ends up giving me 1/7. Okay, so negative exponent flips to the denominator, rewrite exponential form in radical form, and simplify. That's one way. The second method, and I want you to make sure you write down both, is to use exponent rules in a different way. So remember, my original problem is 49 to the negative 1/2. So notice what they're going to do here. They're going to say, okay, well, 49 is 7 squared, and I'm raising that to the negative 1/2 power. Power to a power, remember I multiply my exponents. 2 times negative 1/2 is negative 1. And then a negative exponent means reciprocal, so 1 over 7. So notice I get the same thing either way I did it, and both ways are legal. Okay, let's try two methods with this one, 32 to the 2/5. My first method would be, okay, I'm going to split up this exponent of 2/5. So that's like 32 squared to the 1/5, right? 2 times 1/5 is 2/5. So I'm just rewriting what it looks like. 32 squared to the 1/5. Well, this 1/5 is a root, right? That 1/5 is like a 5th root of 32 squared. The 5th root of 32 is 2. And so I end up with 2 squared, which is 4. I think they wrote it out a little bit weird here, but another way to write this is to say the 5th root of 32, and that squared can go outside the radical instead of under. It's equal both ways. So you end up saying, okay, the 5th root of 32 is 2, and 2 squared is 4. Maybe that's a little bit clearer than the way that they wrote it out here. All right, I want you guys to try, oh, sorry, I almost forgot about the second method. The second method would be to start by writing 32 as 2 to the 5th, and actually in this case I think this would probably be easier. If you notice that 32 is a perfect 5th root, right, then I can multiply those exponents. 5 times 2/5 is 2, and then 2 squared is 4. So this section is all about understanding your radical and your exponent rules and being able to rewrite things in different ways to simplify as quickly as possible. All right, you guys try this one. Okay, your answer here should be 1/5. And here's the work for both methods, how you would get to 1/5. Okay, try this one, 16 to the 3/4. Your answer here should be 8. And there's the work for both of the methods to simplify that expression. Okay, in general, and you probably noticed this from an example like what we did back here in the check your progress. Oops, sorry. 16 to the 3/4, notice that that numerator 3 ends up being the exponent underneath the radical, and the denominator 4 ends up being the index. That's actually always going to be true. And so for any non-zero number b, if my integers are x and y, if I have b to the x over y, right, that denominator of my fractional exponent becomes the index, and the numerator of my fractional exponent becomes the exponent on the b underneath. And just like I said before, the exponent can go inside the root or outside the root, and it will be the same thing either way. So for example, 27 to the 2/3, the 3 becomes my index, and the 2 becomes my exponent. So that gives me, I can do the cube root of 27, which is 3, and then 3 squared is 9. All right, so let's take a look. Actually, we're going to skip this example, and we're going to come over here to example 4. So we're simplifying y to the 1/7 times y to the 4/7. When I multiply powers with the same base, remember I add the exponents. It's the same even when the exponents are fractions. It doesn't change. So this is going to give me y, and I'm going to add my exponents. 1/7 plus 4/7 gives me 5/7. And I can just leave it like that, because even if I rewrote it in radical form, which would be the 7th root of y to the 5th, I can't really simplify that. There's nothing else to do. So it's fine in this case to leave it in exponential form. Okay, x to the negative 2/3. We're going to start again. Remember that the exponent rules are still the same, even when the exponents are fractions. So negative exponent means reciprocal, so this is 1 over x to the 2/3. The problem is that this means 1 over the cube root of x squared, and we are not allowed to leave radicals in the denominator. So what I really want is for my denominator to be just x by itself, right, without a fractional exponent. So notice what we're doing here. To make it be x to the 1st, this is x to the 2/3 is what I have, so I need to multiply by x to the 1/3, so that when I add 2/3 plus 1/3, I get 1, right? So notice here I multiplied the numerator and the denominator by x to the 1/3. And so that leaves me with x to the 1/3 over x. And that is simplified because there are no radicals or fractional exponents in my denominator. Okay, you guys try this one. Okay, hopefully that was pretty fast. You're just multiplying, so you add the exponents. 1/5 plus 2/5 is 3/5. Okay, try this one. This one turns out to be C, and there's the work for that one. So notice I multiplied numerator and denominator by y to the 1/4, so that in the denominator I will get an exponent of 1, and there are no more radicals. Okay. All right, now we're going to get into some simplifying that's a little more complicated than what we've done before. And the reason is, for example, here in our first part of example 5, notice in my numerator I have a 6th root, and in my denominator I have a cube root. So the way things are now, I can't simplify either of those. The cube root of 2 can't be simplified, and the 6th root of 16 can't be simplified. And I can't divide them because they're different indices. But this is where changing from radical to exponential form will actually come in really handy, and it's going to allow us to do some simplifying that we couldn't do before. So first I'm going to rewrite the 6th root of 16 as 16 to the 1/6, and the cube root of 2 as 2 to the 1/3. And now I'm going to see if I can figure out a way to rewrite one of these so that they'll have the same denominator in their fractional exponent. Well, this is where it's really important to recognize your powers, because you should recognize that 16 is not only a perfect square, but also a perfect fourth. So I can rewrite 16 as 2 to the 4th. When I do that, 4 times 1/6 is 4/6, right? 4 times 1/6 is 4/6, which reduces to 2/3. That's why this now says 2 to the 2/3 over 2 to the 1/3. So notice both of these are now cube roots. So based on my exponent rule, I can subtract my exponents when my numerator and denominator have the same base. That's why we went with 2 to the 4th instead of 4 squared. Now this has a base of 2 and this has a base of 2, and now I can use my exponent rules on the numerator and denominator. 2/3 minus 1/3 is 1/3, and 2 to the 1/3 is the cube root of 2. So it turns out that that problem does simplify down to the cube root of 2, but you wouldn't notice it if you couldn't put it in exponential form. All right, let's try this one, the 6th root of 4x to the 4th. Again, x to the 4th, there are only 4 x's, 4 is 2 squared. It doesn't look like we can do anything the way that it is, but if we rewrite it with exponents, and then start to play with our powers inside, you'll see that some cool stuff happens. So 4x to the 4th, all to the square root, or all to the 6th root, sorry, is all to the power of 1/6. So I'm going to see if there's a way that I can rewrite 4 and x to the 4th as powers. So I know that 4 is 2 squared, right? That's an obvious one. So I'm going to see, can I rewrite x to the 4th as something squared? Yes, I can. It's x squared squared. So then that's basically 2 squared to the 1/6. So I have to multiply this exponent by the 1/6, and I'm going to multiply this exponent of 2 by the 1/6. So I have 2 squared to the 1/6, which gives me 2 to the 2/6, and x squared squared to the 1/6. So I multiply those based on rules of power of a power. And notice now they both have the same exponent of 1/3. So I have 2 to the 1/3 and x squared to the 1/3. So since they're both to the 1/3, 1/3 power is a cube root. So now I have the cube root of 2x squared. So this actually does simplify. It doesn't come out of its radical, but it reduces down to the cube root of 2x squared, but only if we use rational exponents. All right, one more to try together before you guys try a few. This is going to be very similar to what we did back in Chapter 4, where we have to rationalize the denominator when the denominator is a binomial. Because remember, this y to the 1/2 means square root of y, so this is like the square root of y minus 1. So I'm going to multiply by the conjugate again. So my conjugate, my denominator is y to the 1/2 minus 1. My conjugate is y to the 1/2 plus 1. Multiply that numerator and denominator. When I multiply my numerator, y to the 1/2 times y to the 1/2 is y. Then I have y to the 1/2 times 1 plus y to the 1/2 times 1. That's where we get the 2y to the 1/2. And then 1 times 1 is 1. And then in my denominator, since this is conjugate, so when I multiply the denominator by its conjugate, I get y to the 1/2 times y to the 1/2, which is y. Remember, my middle terms cancel out when it's conjugates, and negative 1 times 1 is negative 1. And that is my final answer because there's no other simplifying I can do. There are no like terms, I can't factor, I can't do any of that. All right, you guys try this one. Okay, your answer here should be B. And there's the work for this one. So remember, when my numerator and denominator have radicals with different indices, I rewrite it with rational exponents, and then I see what I can do. So here I rewrote 4 as 2 squared. 2 times 1/4, right, gives me that exponent of 1/2, and then in this case, 2 to the 1/2 over 2 to the 1/2 is 1. Okay, you guys try this one. The answer here is A, and there's the work for this one. Notice I rewrote it with rational exponents, and then I saw if I could somehow get both of the things in here to the same power. So 4 squared and x squared. Then when I multiplied the exponents, I got 1/3, which means they're both under a cube root. All right, last but not least, try this one. Okay, your answer here should be A. And here's the work. Notice I'm multiplying by the conjugate of the denominator, right? So since the denominator is x to the 1/2 plus 1, I multiply by the conjugate of x to the 1/2 minus 1. And then here's the work for multiplying that out. All right, so a summary, if I have an expression that has rational exponents, it's simplified if I meet all of these conditions. No negative exponent should be left. No exponents that are not positive integers in the denominator. So that means no negative exponents and no fraction exponents. It can't be a fraction inside of a fraction, and I have to reduce the index as much as possible, like we did in some of our earlier examples. That's the end of this section. I'll see you in class to practice.